All right, friends, here we go. Last day on metabolism. We're several steps into the citric acid cycle. This is how we take acetyl-CoA and convert it into CO2. You can sort of pay attention to the beginning of what kind of oxidations you need to have happen. We got to oxidize. We got to get this carbon that's in the thioester is bonded to 3 heteroatoms. We need it bonded to 4. So that's going to be one oxidizing reaction. Then this carbon that's bonded to 3 hydrogens, that's going to need 4 new heteroatom bonds. So you're going to see that the citric acid cycle ends up generating 4 new oxidizing equivalents. And the story of the citric acid cycle is simply first incorporating acetyl-CoA into a larger molecule, then moving the alcohol around so you can get an alpha keto acid or a beta keto acid that you can decarboxylate. I showed you several steps last time. The first is the aldol reaction in thioester hydrolysis catalyzed by citrate synthase. Recall that an enzyme removes the alpha proton. You do the aldol reaction to make a new bond with a carbonyl carbon. You protonate the tetrahedral intermediate. And at this stage, nature hydrolyzes that CoA thioester to commit acetyl-CoA to the citric acid cycle, because ultimately you start with a thioester, but you end with a carboxylate. That's level 1 to level 4 reactivity. Excuse me, strongly downhill, and that commits acetyl-CoA to the citric acid cycle. This molecule citrate, recall you lose track of which carbons come from acetyl-CoA versus which come from oxaloacetate, because this arm and this arm of citrate are identical. If we wanted to decarboxylate any of these carbons in citrate, you got a problem, and that is the OH group is there, but you can't oxidize it because it's on a tertiary carbon. So the second step of the citric acid cycle is to move the OH group over. Now, as I told you, there's kind of a weird way of counting citric acid cycle steps. Some people count intermediates, some people count enzymes, and a couple of the enzymes catalyze multiple reactions. So I'm going to count intermediates. You're welcome to count however you want. The enzyme aconitase catalyzes the dehydration of the alpha or the beta hydroxy acid. Base removes a proton, electrons kick down to make a double bond here, and water protonates the OH as it's leaving. That gives you cis-aconitate, which, as I pointed out last time, is doubly alpha-beta unsaturated. That is, this carbon is alpha to the blue carbonyl carbon, but beta to the pink carbonyl carbon. Yes? Oh, that's fun. This computer's local host name is already, I don't care. Let's just turn off the Wi-Fi, and then we're fine. Whoops. Can you all see that? You're good, right? Okay. So, if water did a conjugate addition on the blue beta carbon, we would just go right back to citrate. And that happens because this step is reversible. But if water does conjugate addition by attacking the beta carbon, the pink beta carbon, then we move the alcohol over. So base removes the proton, OH attacks pink beta carbon. We protonate the resulting intermediate with an acidic side chain from the enzyme active site. And that generates isocitrate, which has the following stereochemistry: a wedge on this carboxylic acid group and a wedge on this alcohol. Isocitrate, same molecular weight, just different connectivity than citrate. And again, this conversion is also catalyzed by aconitase. The benefit of isocitrate is now we got a secondary alcohol, which can be oxidized because there's a hydride, there's a hydrogen on the secondary alcohol that could potentially be accepted by NADH. The other beauty of isocitrate is this OH is alpha to one carbonyl and beta to another. By one oxidation event, we simultaneously could make a beta keto acid and an alpha keto acid, and those are the two structural patterns that we need to do decarboxylation. Decarboxylation is one of our main goals of the citric acid cycle because we need to convert acetyl-CoA into 2 molecules of CO2. So the next reaction we talked about is exactly what you would expect. It's isocitrate dehydrogenase. The base removes the proton, electrons kick down, hydride gets delivered to NADH in the usual way, and that gives us oxalosuccinate, which is a beta keto acid and can undergo spontaneous decarboxylation. By the way, this isocitrate dehydrogenase has taken NAD plus and generated a molecule of NADH, and so that's one sort of energy-rich profit molecules on our ledger as we go through this process. So let's show you the spontaneous decarboxylation of the beta keto acid. Electrons on the carboxylate oxygen kick down to make CO2. Normally, we might show these electrons going on to the alpha carbon to make a resonance stabilized intermediate. An equivalent alternative would be to show the electrons going out onto that carbonyl oxygen. That's just a resonance structure of the enolate. But to save time and space, we're going to just protonate the enolate with an acidic group from the enzyme side chain that facilitates the decarboxylation. When that happens, again, we lose the pink carbon as CO2. We started out with 6 carbons, now we're going to have 5. And the resulting molecule looks like this. A 5-carbon chain, carboxylates on either end, and a ketone at the alpha carbon. So this molecule is called alpha keto glutarate. Glutarate is a name for a 5-carbon diacid where the acids are on either end, and then the alpha keto tells you there's a ketone on the alpha carbon. All right, so I will call this steps 4 and 5. The dehydrogenation step I will call step 4. The decarboxylation step I will call step 5. Some textbooks or web pages don't even show oxalosuccinate as an intermediate because it spontaneously decarboxylates. I want you to show it as an intermediate because it's only when you draw its structure that you realize, hey, a beta keto acid, that can decarboxylate, and it makes chemical sense. Okay, questions about that step? So that's one of the molecules of CO2. Some of the CO2 you are exhaling comes from that reaction. Right, every time you sigh from now on, there goes another oxalosuccinate. Right? Maybe that can be your mantra as you're meditating. Oxalosuccinate. There it goes. People are going to look at you funny, but at least you'll know your citric acid cycle. All right, step 6 is just exactly what you would expect it to be. You now have an alpha keto acid, and the other alpha keto acid we have seen before was pyruvate. Do you recall just a day ago or a couple days ago we went through the pyruvate dehydrogenase complex, and pyruvate is an alpha keto acid. And in the process, pyruvate loses that portion of itself as CO2, and the remaining portion becomes acetyl-CoA. This carbon gets oxidized to a thioester, and the enzyme uses NAD plus to accomplish this, generating a molecule of NADH. It also requires the coenzyme A-thiol. And then also as cofactors, as you recall, are involved thiamine, lipoate, and FAD. So that was kind of complicated. We spent most of the day talking about that. So you can go back to the last lecture to review how that process happens. Alpha ketoglutarate, like pyruvate, is an alpha keto acid. And so step 6 of the citric acid cycle is going to mirror what you saw for the pyruvate dehydrogenase complex. That is, you're going to start with alpha ketoglutarate. And you're going to use this time a related complex called the alpha ketoglutarate dehydrogenase complex. The cofactors and the ingredients or reagents, as it were, are going to be exactly the same. You'll need the coenzyme A-thiol. You'll need NAD+, and it will be converted into NADH. You will likewise need thiamine to serve as an electron sink during the decarboxylation step, lipoate to oxidize the intermediate after the decarboxylation to the thioester, and then FAD and NAD+ ultimately to reoxidize the lipoate disulfide, lipoate thiol to the lipoate disulfide. When you're done, the green carbons on alpha ketoglutarate are coming off as CO2, and then the blue carbon on alpha ketoglutarate is going to get oxidized to the thioester oxidation state. 1, 2, 3, 4. And I'm kind of running out of space, so let's slide that over. And this molecule now has 4 carbons, and it's called succinyl-CoA. Succinate is the 4-carbon acid, diacid that has acids on either end. So you can see the analogy to what you saw before for the pyruvate dehydrogenase complex. So I'm not going to push arrows through that. You've got the arrows for that in what we talked about last time. Okay, questions? Yeah.
So just to understand, these 2 reactions that we're seeing here are the summarized versions of what we learned in class last time?
That's right. Yeah, so you've seen this last time. Last time we did the decarboxylation of pyruvate, and what I'm saying is the mechanism for alpha ketoglutarate, the enzymes are different, but they're highly similar. The mechanism, the arrow pushing will be exactly the same. So yeah, see the April 9th lecture for the arrow pushing on that. All right, so we've lost both equivalents of CO2. Now our goal is going to be to get from this 4-carbon diacid back to the place where we started, and the place where we started was a 4-carbon, 1, 2, 3, 4, diacid with a ketone on the alpha carbon. So the remaining steps are just going to be about completing the circle. Nature's pretty efficient, and one of the things that you observe about succinyl-CoA is that it is a thioester. And as you know, thioesters are level 1 reactivity. Nature could hydrolyze that thioester, but that would be, to hydrolyze it and do nothing else would almost be a waste of free energy, because you'd be going from something that's level 1 reactive thioester to a carboxylate that's level 4 reactivity, very, very stable and not that useful. So what we do is we're going to use an enzyme to recover a molecule of ATP or an ATP equivalent at this stage. So we're going to use GDP, guanosine diphosphate, and a molecule of inorganic phosphate, and that's going to generate a molecule of GTP. And the enzyme that does this is called succinyl-CoA synthetase. It's actually named for the reverse reaction, which, you know, why, but, and the reason that things are often named for the reverse reactions is because scientists didn't know how this worked to begin with. They discovered a reaction that ran in one direction, and then they discovered that actually metabolically it's also important to be able to run in the other direction. So So sometimes the names are named for the backwards reaction, as I said before. This 4-carbon diacid is called succinate. Notice that we're going to take a thioester and we're going to use it to make a phosphoanhydride bond in GTP. So we're exchanging one level 1 reactivity molecule for another. The mechanism here is going to be very similar to things that you've seen before. So we'll take a molecule of inorganic phosphate, or PI. Lone pair electrons on the phosphorus will attack the carbonyl carbon. We'll get a tetrahedral intermediate. I'm going to assume that you can draw that tetrahedral intermediate and then draw the products that come from that. That's simply a nucleophilic acyl substitution reaction. As a result, coenzyme A leaves, and we end up with this acyl phosphate intermediate. And you have seen acyl phosphates before. They look like an anhydride on the carbon side. They look like a carbon anhydride on the carbon side and a phosphoanhydride on the phosphorus side. The point really is that in the acyl phosphate, both the phosphorus and the carbon are electrophilic. If the coenzyme A thiol were to attack the carbonyl carbon, you would go back to starting materials. But instead, if the beta phosphoryl, if the oxygen on the beta phosphoryl group of GDP attacks the phosphorus, then you end up with this 5 pentavalent intermediate where phosphorus is attached to 5 different things. And the carboxylate group there acts as a leaving group, which is pretty reasonable since it's level 1 reactivity. Electrons will kick on one of the oxygens, will kick down and kick off the carboxylate. This phosphorus then becomes the gamma phosphate group on GTP. And that's going to be one of the energy-rich molecules on our ledger that will count as sort of yield from the citric acid cycle. All right. So now comparing where we need to be versus where we are, as I said, we want to get back to oxaloacetate. But right now this carbon where there's a ketone only has hydrogens on it. And so we're going to need to oxidize that alpha carbon to have the ketone there. And that's going to take the remaining steps of the citric acid cycle. All right. So 8 is going to have succinate react with 4 carbon diacid. Oops, sorry. The enzyme that oxidizes succinate is unsurprisingly called succinate dehydrogenase. The thing that does the oxidizing is FAD, and I'm not sure why it's FAD instead of NADH, instead of NAD+. The mechanism is basically going to have a basic group in the enzyme side chain is going to remove one of these alpha protons. At the same time, electrons are going to kick down, and we're going to eliminate this hydride. Now, hydride is not a good leaving group, but it can be kicked off if the oxidizing agent stands there really close and ready to receive the hydride. So here is the structure of FAD. Hydride is delivered to this nitrogen that's sort of at the para position relative to the other nitrogen. Then electrons kick down here, and then the other nitrogen gets a proton from solvent or from the enzyme. You can tell that this is an oxidation reaction because it decreases the number of carbon-hydrogen bonds in our product. We go from an alkane to an alkene, and this 4-carbon alpha-beta unsaturated diacid is called fumarate, which always sticks in my mind because I learned on my mission the Spanish word that's for the infinitive of to smoke, which is fumar. And so I don't know why that sticks in my head. Somebody looked it up. Somebody last time I taught the class was like, I don't know why it's called that. I wonder if it has anything to do with smoking. And he looked it up. Somebody looked it up, and it comes from the name comes from some plant, and I forget the story. So I learned it was interesting, and then I forgot it. So if one of you wants to look it up and then remind me, that's fine. But anyway, fumarate. The key functional group in fumarate is the alpha-beta unsaturated carbonyl compound, which sets us up for a conjugate addition reaction to put the oxygen in the right place. So the great thing about fumarate is that it's alpha and beta unsaturated in both directions. So we can have water add to the beta carbon, and either of those two identical carbons is the beta carbon. So let's show you how this will happen. Let's add to the blue beta carbon. We'll do exactly the same as we've done before for other conjugate addition reactions, like the reaction to make isocitrate. We'll have a base from the enzyme active site remove the proton from water as it attacks. It'll attack the beta carbon. Instead of showing an enolate forming, we'll just show the enolate getting protonated by some acidic group from the enzyme active site, and that creates the secondary alcohol that has this particular stereochemical configuration. That configuration is controlled by the enzyme, and to reflect the fact that this is an antio-pure, meaning just one enantiomer, this molecule is called L-malate. And the enzyme that does this, catalyzes this reaction, is called fumarase, which is just the enzyme that acts on fumarate. Okay, and at this point, if you compare where we're trying to get to, which is oxaloacetate, you could totally predict what the final reaction of the citric acid cycle is.
So there are 2 enzymes to that step?
No, fumarase is step 9.
Okay, and L-malate is just...
L-malate is the name of this molecule at the end, yep. So for step 10, all we need to do is oxidize that secondary alcohol in L-malate to become a ketone, and then we will have completed the cycle to make the starting material for the citric acid cycle, which is oxaloacetate. The enzyme that does this is called malate dehydrogenase, and you're going to use a molecule of NAD+, get a molecule of NADH out, and this is just basically, I won't draw the mechanism for you because you've done an NADH-based oxidation again. In words, you'd have a base remove this proton, electrons would kick down, and NAD+ would accept this hydride in blue. That gives us oxaloacetate as our product, and there we will have completed one turn of the citric acid cycle. So there it is. You're done with that particular thing. And in 2 days, done with the class, so it's going to be all right. We're going to make it. All right, questions about any of those steps we talked about? Yes?
What was step 5?
So step 4 and 5 we showed together. We oxidize the alcohol in isocitrate in isocitrate to form the ketone in oxalosuccinate. And then that beta keto acid spontaneously decarboxylates. I call that step 5, and that gives you alpha ketoglutarate. Okay, others? Yeah.
Sorry, on step 10, did you say it deprotonates the alcohol group or the alcohol?
Yeah, you deprotonate the alcohol group. I mean, oops, that was not the eraser that I wanted. Oops, there we go. No, sure. Yeah, it would look like this. Remove the proton, electrons kick down, and hydride gets delivered to NAD+. Yep, go ahead.
So for 1 molecule of glucose goes through glycolysis twice, you get 2 pyruvates.
No, 1 molecule of glucose goes through glycolysis once to give 2 pyruvates. Yep.
And then both of those pyruvates go through.
Both pyruvates go through this. Yeah. And we'll summarize that in just a little bit. What else? Yeah.
Do we have to memorize all the names of the enzymes
Enzymes, yes.
and the names of the products?
Yes. Again, you can brute force memorize it, but just as it's easier to remember words when you've got a tune to go with them, it's easier to memorize the citric acid cycle and glycolysis when you can hear the melody of what's trying to happen here and you can sort of see the chemical logic. With enzyme names, if you know what the reaction is, you can probably pick the correct enzyme name out of a lineup. If you know what a dehydrogenase is, for example. And then in terms of memorizing the structures of the products, if you have an idea of why nature's doing what it's doing, that can help too. Okay, others? Yes?
So these steps 1 through 10, they're part of the citric acid cycle, but not the whole thing?
They are all of it.
Oh, this is
Yes,
the entire
this is from 1 through 10 is the citric acid cycle.
May I ask then, what does exactly this oxaloacetate do for us?
It's the entry point, because when you make oxaloacetate, that's what, in the first step, accepts acetyl-CoA.
And that's why it's a cycle.
Yep, that's why it's a cycle. The course of the citric acid cycle is one eternal round. And it's difficult to tell because of that where it begins and ends, yeah.
And as we're going through the cycle, we're pumping off CO2.
Yep,
And we breathe that out, but we're also, reducing NAD
Yes.
plus and FAD, and then that is powering the
electron transport chain, yeah. So to summarize what we did in the citric acid cycle, you turn acetyl-CoA into 2 molecules of CO2. Along the way, you make 3 molecules of NADH, you get 1 molecule of FADH2, and you get 1 molecule of GTP. All right. And we'll take these. GTP you can exchange for ATP easily. You can use GTP to phosphorylate ADP directly. So it's fully equivalent to 1 ATP. And then in the electron transport chain, each molecule of NADH on average leads to 2.5 molecules of ATP. So for 3, you're going to make 3 times 2.5, what? 7.5 ATPs. And then from 1 FADH2, on average, you get 1.5 ATPs per FADH2. So that leads to overall, why is the math always hard? Is that 10? Yes. Arithmetic is not my thing. ATP. All right, so one of the things we can do actually to summarize everything that we've done so far is to consider what the total yield of glucose is from glycolysis through the pyruvate dehydrogenase complex and through the citric acid cycle. So if we take 1 molecule of glucose and we do glycolysis, recall that in that process, we get out 2 overall molecules of ATP. Now we invested 2 and we get out 4. So I'm just doing the math, and -2 + 4 is 2. See, that was arithmetic I could do fast. Then we also get in glycolysis 2 molecules of NADH out, which we can exchange for 5 molecules of ATP. Then for each molecule of glucose, we get 2 of pyruvate. And then in the pyruvate dehydrogenase complex, we do oxidative decarboxylation to get acetyl-CoA. Each time we go through the pyruvate dehydrogenase complex, we make a molecule of NADH. We're doing that twice here, so we should get 2 NADHs out, which is equivalent to 5 ATP. That gives us 2 molecules of acetyl-CoA. And in the citric acid cycle, as you've just seen, for every molecule of acetyl-CoA, we get, in the pyruvate dehydrogenase complex, we also get 2 molecules of CO2. For every time through the citric acid cycle, we get 2 molecules of CO2. So 4 if we start with 2 acetyl-CoAs. And then we also make what's shown here, 3 NADHs, 1 FADH2, and 1 GTP. Let's see, since it's twice through for 2 acetyl-CoAs, that's 6 NADHs, that's 2 FADH2s, and that's 2 GTPs. Of course, the 2 GTPs are exchanged directly for 2 ATPs. Then let's see, the 2 FADHs, that should be 3 ATP, and then the 6 NADHs, carry the whatever, 15. Didn't successfully do the arithmetic in my head, I looked at my notes. All right, so 1 glucose, 6 carbons. All of those carbons end up as CO2. 2 CO2 from the pyruvate dehydrogenase complex and 4 from the citric acid cycle. And if you want to add up all the ATP, you can check my arithmetic, but there are, for every molecule of glucose you metabolize, 32 ATPs per glucose. All right. So that's kind of cool. That's a lot of ATP, and you use that ATP to do work. ATP drives processes. ATP hydrolysis, as it were, is mostly just transfer of phosphate groups from one place to another to do work. That's how your muscles move. That's how a lot of other things happen. But we can do some sort of back of the envelope calculations to get a sense for how much ATP you need to use every day just to stay alive. So on average human needs how many calories a day to be functional? I'm not talking about surviving without death. I'm just talking about having a normal day. 2,000 is a good rule of thumb, right? So average caloric needs for a human is around 2,000 calories. Now the big C calorie on your nutrition labels is our kilocalorie. The average free energy change for ATP hydrolysis, which drives the things you do when you're spending those 2,000 calories, is about -7, anywhere from -7 to -15 kilocalories per mole. So we can actually get a range for how many moles of ATP you need. and that's just dividing, but I've already done the math for you. So it's anywhere between 130 to 300 moles of ATP. That's a lot of ATP molecules. If you know the molecular weight of ATP, this is between 66 and 152 kilograms of ATP. Now, in the United States, we deal mostly in pounds, so you may not have an idea of what a kilo is, but average human body mass is in that range. So, and you know that you're not actually composed of 66 to 152 kilograms of ATP. If you're like me, you're composed of a ton of water, some muscle, and then a fair number of triglycerides that I'm carrying around the middle. So that means that you don't actually have all of that ATP in your body to spend one at a time. So we can actually figure out how many times your body has to recycle through that to get to take care of your energy needs. But before we do that, just on this conversion of ATP per glucose, if all of the ATP you make came from glucose, and if you were going to gain your nutrition by spooning glucose into your mouth, glucose and only glucose, which is like yuck, but suppose you're on the opposite of a sugar cleanse, which would be like a sugar exclusive diet or something like that, your daily glucose needs would be between 4 and 9 moles of glucose, just dividing these numbers here by 32. And that would look like anywhere between 0.7 to 1.7 kilograms of glucose. So that's a lot of honey or a lot of high fructose corn syrup to work your way through. And of course, we've talked about triglyceride metabolism. We haven't talked a lot about protein metabolism. You can get ATP from a lot of sources. It all gets funneled through acetyl-CoA. So you can actually figure out about how much ATP you have in sort of the average human, how much ATP is in the average person. To do this, you need to know the average ATP concentration, which I looked up, and it took me a while to find a source that seemed accurate. The number I came up with was between 3 and 4 millimoles per liter in you. So then you need to know your volume to calculate how much ATP you have. And you can do that by hopping into a tub full of water and seeing how much water you displace. I didn't actually do that. I just looked up what the average human volume is. My volume is probably larger because of the triglycerides, but what are you going to do? 42 liters on average human volume. So that means you have somewhere between, if I'm going to do that, I need to lean into it. That's better. 126 to 168 millimoles of ATP. So now do the math. You need to process 130 to 300 moles of ATP, but you only have 126 to 168 millimoles. That means that every molecule of ATP in you is recycled. That means rephosphorylated in the electron transport chain or in substrate level phosphorylation 1,000 to 2,000 times. So if you thought your job was boring, imagine being ATP where you get phosphorylated, you go transfer the phosphate and then back to the mitochondria again 1,000 to 2,000 times a day. That's how efficient your cells are, your mitochondria are. And all of that we need just to live and breathe and think and run and all of that stuff. All right, the other thing we could do is now combining what we know about fatty acid metabolism and the citric acid cycle, get a sense for how much more ATP you get from a fatty acid and a triglyceride. So we'll do that real quick. Somebody at 9 a.m. said, how much of this math do I need to memorize? And I'm like, math, really? Have you taken any of my exams? If you can count and add, that's probably fine. I'm not, you don't have to memorize the molecular weight of ATP. This is just back of the envelope calculations to figure out an interesting story. So you should have a sense for how much ATP and NADH and FADH2 and GTP is made in metabolic processes, and you should definitely know the exchange rate in the electron transport chain. Other than that, you should be able to figure out what you need to, you should be able to figure out anything I might ask you. So let's suppose we have a 16 carbon fatty acid, 2, 4, 6, 8, 10, 12, 14, 16. We get that from hydrolysis, lipase-based hydrolysis of a triglyceride. This is a 16 carbon fatty acid. Preparing it to become the 16 carbon the 16 carbon fatty acyl CoA, if you recall from a couple of days ago, requires the investment of basically 2 equivalents of ATP. So by generating the CoA thioester out of the fatty acid, you lose 2 molecules of ATP. Breaking that fatty acid up into acetyl-CoA, we learned, was called beta oxidation. For a 16 carbon thioester, how many times do I need to go through beta oxidation? 7. You're going to get 8 units of acetyl-CoA, but you only need to do fatty acid beta oxidation 7 times because there's only 7 bonds between the 2 carbon units. So we are going to get 8 molecules of acetyl-CoA out. We'll do fatty acid beta oxidation 7 times. And you could go back to your notes and see that each time through fatty acid beta oxidation, we get 1 molecule of NADH and 1 molecule of FADH2. And since we're doing that 7 times, that's what we gain from beta oxidation. Then, in the citric acid cycle, as you learned, each molecule of acetyl-CoA generates 3 NADHs, so 8 times through, that would be 24 NADHs. 8 times through would be 8 FADH2s and 8 GTPs. And with all of this, GTP we're going to say is equivalent to ATP. So, and that's going to generate 8 molecules of CO2, and then let's figure out the exchange of all of those ATPs, or NADHs and FADH2s for ATP in the electron transport chain. So we get 8 ATPs out from GTP, but we were down 2 to begin with. So our first sort of subtotal is 6 ATPs. Then overall, I'm counting, 31 NADHs. So somebody want to see how many ATPs you get from 31 NADHs? Because I don't want to do that math. And somebody else see how many how many ATPs you get from 8 FADHs. 77.5 for the NADHs, and then for the 8, 1.5, 12, okay. Oh, okay, the number, okay, thank you for that. Sorry about that. It's 7 plus 8. See, arithmetic, just not my thing. Now what is it? 22.5. Okay. And then if you add that up, it's like, that looks like 99.5. Oh, 100 plus 6. 106 molecules of ATP. All right. Now that's where I ended at 9, but we've got enough minutes to do the whole triglyceride. Shall we? So remember, 106 ATPs from a 16 carbon fatty acid. Now, let's envision a triglyceride where each of the fatty acid chains has 16 carbons. So overall, that would be 318 just from the fatty acid portion. 318 ATPs from fatty acids. What about the glycerol? We learned that to make glycerol, we first phosphorylate it, so we make 3-phosphoglycerol, and we do that with a kinase, so that's -1 ATP, and then we oxidize to dihydroxyacetone phosphate, and that is, I think that was NADH. Pretty sure that was NADH. Okay. All right, now that intercepts glycolysis midway through. So we're going to have to briefly remember what happens to dihydroxyacetone phosphate. It gets isomerized to glyceraldehyde 3-phosphate. We're going to have to look it up, aren't we? Glyceraldehyde 3-phosphate gets
It gets
oxidized to 1,3-bisphosphoglycerate, and that generates an NADH, right? And then 1,3-bisphosphoglycerate goes to 3-phosphoglycerate, and we generate an ATP. 3-phosphoglycerate goes to 2-phosphoglycerate, goes to phosphoenol pyruvate, goes to pyruvate with ATP. All right. So 1 molecule of glycerol. Let's see, overall, we've got 1, 2 of NADH, and 1, 2, -1, so 2 NADH, and what is it, 1 ATP? And then we've got to do pyruvate through the pyruvate dehydrogenase complex and the citric acid cycle. We're moving fast, but we're just trying to get a number at this point. Pyruvate generates, let's see, where did we go? There it was. Each molecule of pyruvate generates 1 molecule of NADH. So there's 1 NADH there, and then a citric acid cycle is 3 NADHs, 1 FADH2, and 1 GTP. So the grand total for all of this is 2 ATPs plus, am I counting right, 5 NADHs and 1 FADH2, which should be 5 times 2.5 is 12.5, and 1.5, 14, 16?
There should be 6 NADHs.
Where?
There's 2 from the glycerol backbone.
2, 4, oh, thank you. Again, arithmetic, not my thing. 6 times 2.5, please help. You're gonna sit here and watch as I flounder. You're like, how does it feel, Dr. Price? How does it feel? All right, so I'm counting something like 18.5 plus 318, 336.5 of ATP from 1 triglyceride. So this is why we crave fats and oils, because they're so energy rich, and this is why we store them, because we can get a whole lot of ATP out of a triglyceride. Okay, that's it for today. We'll move on to chapter 28 next time. I will see you Monday. Yep, see ya.